All right, everybody, here we go. It's another machine learning design pattern. This one is based on a product that may be fictitious, or it might not be, that was worked on by somebody you might know, or maybe somebody you don't know. It's a computer vision system. Let's pretend it's a toaster. Why do you need computer vision in a toaster? Who knows? But let's just talk about it as if it's a fancy toaster of the future, or maybe it's something else. Maybe it's an in-house assistant or a game system. Don't worry about it. But what we're going to talk about today is Corpus Centric learning and how this as a design pattern, distinct from the closed loop design pattern, is another great way to make progress on putting machine learning into your system. Now, remember, we talked about implementing with machine learning and, the intelligence creation environment. Then you have to do intelligence management, which figures out which version of the intelligence should I deploy and how do I make sure everything that needs to get deployed gets deployed together. Then there's the intelligence runtime. In a closed loop system, you would have this feedback loop, but often you'll find that you have a really poor ability to get telemetry. Maybe not even like a poor ability to get telemetry, but it could just be poor for training in that you can't get implicit labels, or there's other reasons that you simply can't use it, and we'll go into that in a second. Well, the corpus-based approach just says, okay, fine, we'll just go collect our own data. We will go and do data collection. We'll run around and find whatever pictures we need for this computer vision system. We'll go get enough of them. Then we'll either sit around, eat pizza, and label them all with the right whys for what we're trying to learn. Maybe we'll pay other people. That's part of the cost of doing a corpus-centric approach. You need to get a lot of data and you need to get a lot of labels. So why would you want to do this instead of using a closed loop? Well, if the concept is very stable, that is, the models that you're trying to predict, like this toaster thing, it's going to look for humans approaching a toaster. Humans are going to look the same today, if 10 years from now, 20 years from now. We're not going to grow extra noses or anything like that. We may change our style, do our hairs a little differently. There'll be a new version of whatever kind of watch that is. But in general, it's going to be a pretty stable concept. And so in that sense, it might be nice to build up a corpus and somehow extract it from the particular version of the product that you're working on and make it available over time. You can do that through a closed loop, or you can do it by explicitly going and building a corpus. Another reason you might want to do this, that you can't get data from usage. So one reason you might not be able to do this is you don't have any users yet. How are you going to ship a closed loop system for something really important when your models are just junk because you have no data to train them on? Well, you're going to have to get a bootstrap somehow, and creating a corpus-centric bootstrap might be a really nice thing to do. Sometimes it's not practical to get training data given the application. We'll look into this a little bit later, but there's two ways to think about it. One is that you just can't set up your user experience to get reasonable implicit or explicit feedback on the concept you're trying to model. That could be because, number one, it's just not clear to users what's going on, or they don't interact with that particular model in your system. They may interact with something a little bit broader that's made up of several models. So it's hard to see how that interaction can feed back to all the different models that are involved. And another thing is that if the time between when the action from the computer occurs and the user notices it gets larger and larger and larger, these things can get really dispersed, and it can be hard to connect actions, implicit feedback, explicit feedback in as training data. And then, of course, there's privacy concerns. You cannot always use your users' interactions as training data, and there are becoming more and more laws in more countries about what rights users have in terms of protecting their data and keeping control over when it's used and how it's used. So you may get into a situation where you have plenty of users, but just for the reasons of the way the application is, or what your users expect, or the return on value that the user feels they're getting from using the product, you might say like, geez, we're just not going to get into that. We're not going to deal with privacy. We are going to go build up our own data set. So we don't have to worry about it. Our users don't have to worry about it. No problem. And then, like I said, with the bootstrap thing, you might need to achieve high quality. You're not going to have a surgical robot that cuts about 50 jugulars, 5,000 jugulars, 50,000, 500, whatever number of mistakes it's going to make, which could potentially be life-threatening, before you've closed the loop enough times to stop doing whatever that potentially life-threatening thing is. And we've talked about in the past how with a poor model is probably too forceful of a user experience. but there's limits to how far you can cover with user experience, and you might need to get your models up to a pretty good point, even to be able to be covered by less forceful, more frequent user experiences. And so what are some disadvantages of the Corpus Centric pattern? Number one is it can be quite expensive. You might have to get tens of thousands of labels before you can get started. Tens of thousands sounds like a heck of a lot, but state-of-the-art computer vision is generally trained on way more data than that. And the labeling that you need to do adds another layer of expense. So Corpus Centric is not just like, let's get 3 people together and spend a weekend getting some data. This is, let's look at the project. Are we building something big enough to warrant spending tens of thousands, hundreds of thousands, maybe millions of dollars to go and get the data so we can launch this product in the first place? And oftentimes you'll look at it and be like, absolutely, this is totally worth it. Let's go start this Corpus Centric process. Another thing that's maybe a little more subtle as to a disadvantage of this is we'll talk more about data labeling, but it's not always clear that somebody in a lab who is not the person, who is not your user, can interpret the situation your user's having well enough to decide what the label should be. And a pretty simple version of this in the spam case is that there's a lot of these newsletters. We'd call them like gray mail, where some people want them, some people don't want them. A person in the lab can't really say, well, hey, this is a newsletter. Many people who get this newsletter say they don't want it. Does this particular user want this particular newsletter right now? So that's one example of things, but there's lots of others. Like you could ask a labeler to annotate data when a user appears to start smiling. Their face is changing. A labeler can see that. It's harder to ask a labeler to label an image when a user is happy, when they're actually happy, because they may be emoting, they may not be emoting. They may be emoting happiness because they're super frustrated. It's just, there's lots of situations where data labelers can't do as well as implicit feedback from your users. You know, pros and cons of a lot of different things. Of course, let's see this as a corpus-centric approach is not set up for ongoing improvement in its purest form. I mean, you could imagine combining corpus-centric with a closed loop, and that's certainly possible, but in its pure form, it's about invest, learn a model, use a model, done. All right, let's talk about what you'd like to do with this fancy computer vision system, the toaster, whatever it is. You're going to have some sensors and a runtime, but there are higher level things of like, what are the capabilities we're trying to accomplish? And one thing you might like to do is detect people. Whatever the image sensor on that device is, it's looking at the world. When a person walks into frame in that image sensor, well, that's an important action because this device is being built to help humans or to interact with humans. You're going to have a model called a person detector. Fantastic. Look at an image, output, is there a person there or not? But just detecting people isn't that super helpful. Maybe, you know, you can initialize and turn on some lights. You might also like to know, well, who is the person? How do I configure the device to work best with them? Or do I grant them access? Or do I make them put in a password before they can start toasting? Whatever it is, you're going to have extra models. To do recognition, you probably want more than just an image that says there's a person in this image somewhere. You might like to say, where in the image is the person? Where are their arms and legs and torso and head? Once you know where their head is, well, what is going on with their face? Do I interpret the image as a face that's looking to the side? Do I interpret the image as a face that's looking up or directly into the camera? How should I interpret that? And then once you know that information, you're better off writing a recognizer to say, well, from this collection of pixels, do I know that that's Jeff or Andrew or any particular person? And then that is all taking place in the runtime, interacting with the sensor, controlling the UI, etc., etc. Identifying people, that would be nice. You don't want unauthorized toasting to happen. You might want to do more than that. You might want to recognize gestures. So if the user is going like, stop, you know, maybe you stop toasting because something's steaming, something along those lines. You could say stop, you could say move on to the next, whatever it is. Maybe you're controlling music, toaster music. You might want to select from a menu. So the user might go that one, pick that one, and just a bunch of different gestures you could imagine. Now, how do we add that here? Well, you'd say knowing where the person is, whose gestures I'm trying to identify are pretty useful. So first we detect if there is a person, then we find, okay, well, that's exactly where they are. Previously we've detected their face, but maybe that's not so useful for these gestures. Now we need to figure out, well, where is their hand? And then you might have gesture models that watch the hand move over time and use the sequence of positions of a hand as input to determine if the user's waving or pointing or something else along those lines. Another thing that you might like to do is say, well, why make them even move their hand? Can't they just smile to stop the toaster, or smile or look? If they're looking away and gesturing, you might say, well, we saw a gesture on that person, but they weren't looking at the device, so maybe we don't register the fact that they made that gesture. Maybe we say, hey, they must have been gesturing to a friend or something along those lines, not to us. So understanding things about the face could be quite important. Who's talking? Are they wearing glasses or not? Because maybe if they're wearing glasses, some other parts of the system don't work as well because things reflect funny, something along those lines. Well, you might add in face models that take the output of the face localizer, which was being used by the recognizer, but then also use them for other things, like to detect, hey, that person there is smiling. They must be happy with what we're doing. That's a positive training example if we were doing a closed loop, something along those lines. Now I'm going to talk through the execution of how the models will communicate with each other. And just to maybe clarify a little bit, there's two concepts that we're touching on here. One is this generic notion of a corpus-centric machine learning design pattern. And the other is a particular computer vision intelligence architecture that lays out the models and how they communicate with each other. And these things are related, but a little bit different. Now we're going to talk about the second one, which is the intelligence architecture, and then we'll bring it back to the corpus-centric pattern and see how this architecture lends or doesn't lend itself to that particular pattern, some of the properties about what's going on here, and then we'll go through how to train the model using the corpus-centric pattern. Now, the toaster's sitting there bringing in sensor input, and it has to decide when it wants to do something. The first thing it's going to do is try to figure out, is there a person in the image that my sensor is pointing at right now? And if there's a plate of cheese and basil and there's no person there, then the system might just say, like, reject that, don't do anything, go to sleep, save power, let's just move on with life. And this can be very nice because the person detector can fail fast, and that whole chain of other models that I showed on the previous slide, which we're going to get to here, you don't have to run them. You can also not process every single frame that the camera happens to shoot. You could say, well, once we've determined there's no human there, wait a while. Wait for motion, wait for 5 seconds, wait for 10 seconds before running the person detector again. And in that sense, you can get things more and more efficient if efficiency is important in your application. But anyway, so the person detector runs. Clearly there's no person there. Exit, throw away the image, exit out, wait. Now another frame comes from the sensor, and the person detector says, well, actually, yep, there is a person there. Now we trigger the rest of the architecture for what's going to happen when we think there's a person. How do we start tracking them, interacting with them, creating the relationship and user experience between this toaster and the user who's standing there? Remember, from our machine learning, our computer vision pipeline, you're probably going to want to, at this point, spend some time normalizing and scaling, or maybe you did that already for the person detector. But whatever case, you want to take this image, say, hey, this is something we need to put into the pipeline. Let's get it a little bit ready. You might imagine that you're going to want to know more than just, is there a person there? You're going to also want to know, where is the person? Or maybe if there's multiple people, which one am I choosing to interact with? You'll often do something like run person localization, and a localization for a person might come back with something along the lines of their skeleton. There's the body and the legs of the person, and that is the part of the image that represents a person and roughly where they are and roughly what they're doing. Person localization, that's great, but that's not enough. At this point, you might take the image and crop it and renormalize, saying, hey, now I have a person out of this broader sensor image. Every person, I want to be scaled to a particular size, no matter how close or far they are from the frame. And I want to do more renormalization. Maybe you want to highlight brightness on their face, or goodness knows what you want to do, but you have a lot more information now, and you can spend some time using that information to improve the signal that you're going to send down to the rest of the execution chain. Then if you're going to do further computer vision, particularly processing the face, you might want to further process that person identification into a more fine-grained face identification. Again, you can now recrop and renormalize just the point of the image that are important to you, and you can run as expensive as you want, or as you need, of let's localize various points around the face and determine generically which way the head is turned. We spoke on the previous slide of that might be very important input to a recognizer that's able to look at the pixels of a face and say, yes, that's Jeff, let him toast, or not, whatever. In general, in a system like this, you may bump into a subcomponent that takes a lot of execution time to run. And you don't necessarily want to stall out the pipeline. So you may take this image snippet, hand it off to a recognizer thread and say, look, in 5 or 10 seconds, that thing's going to tell me who it is. Meanwhile, let's just, start the interaction doing only safe things that are possible without having to have the user log in to make progress. Another mini pattern within this, like what are we going to do with this face, is you might say, well, all of this detection localization, that's pretty darn expensive. But my application is working with the user's face or their hand or some particular part of the user. And you might want to kind of cut yourself off from this long, slow, expensive chain and start to do more fine-grained processing on the part of the image that you're interested in. So at this point, you could imagine doing a fast face tracker. And what that would do is take in this image as an initial input, and it would take the previous image, the previous points, which is what we were just talking about there, and then it might take in the current image. So if the sensor gets a new image and I have moved like a little bit to the left there, then you might pass in this image, you might pass in a slightly larger image with, whatever the pixels are, like a region around the previous image with a mapping so the device knows how to align these two images. And then you want this fast face tracker to output a new crop on where the face is in the new image with the points updated. In general, the speed that a human can move at compared to the speed that a camera can take a picture at, you can't go too far in 1 frame or 2 frames or 10 frames or maybe 10 frames. But in a small number of frames, you're really not going to move too far unless you make a gigantic move. So it's often quite possible to get an extremely fast incremental localizer instead of running the base localization system from scratch. And then, of course, if this model ever outputs a new face with a low enough confidence value, you could say, well, okay, whatever, we tried to save some time, but let's go back to the beginning and start again. That's another thing that you might do to keep your computer vision system. And then all of that I just spoke about results in a reduced key points but high efficiency version of the face. I don't know if you can see, but this one has like 5 points on it, whereas this one had 10 or 50 or 100 points or whatever the heck it is. But you've just created this other thread that's processing you just the information you need for specific models that you're going to try to create. And if those models happen to be about processing the face, for example, as soon as the user smiles, stop the toast, something along those lines, or make sure that the user is talking to the device before you run the speech recognition and interpret it as a command. Well, you could have a whole series of face models that take this as their input to process all sorts of different parts of the face. And you might even say that in your architecture, you would say that all of these face models must use the same featurizer. There's certain filters that you run on the face, certain Gabor wavelets or gradients that you look for, or a neural network, some whatever. You could say that all of these run that featurizer, no matter how you got it, whether it's handcrafted or from a neural network. And then they're followed up by very simple models that combine all that information into a prediction about the concepts of interest. And in a computer vision system, you might have extreme constraints, which would require this architecture. So you'd say a new frame comes in, we do the incremental track to get the right pixels, we pass it to this highly optimized featurizer that's shared across multiple models. Each of those models runs something very simple, like maybe even a logistic regression at this point to combine these complicated features. And then you're able to, with several milliseconds per person per frame on reasonable hardware, keep the predictions that you need available. Okay, well, that's an example of execution. Of course, I've left out many things that you might also want to do, but this is just to get us started. And some of the properties of this are that there are lots of models trained on the same data. That's an interesting thing. It's a positive case for using a corpus-based system because that means each particular piece of data you collect could potentially be used in multiple places. We'll get into some of the ifs, ands, and buts about that. Downside of this intelligence architecture is that there is tight coupling between the models. The output of one model really affects the input of another model and what that downstream model has to do. And when we talk about training, we'll see some of the implications of that. In this particular case, it's difficult to close the loop on labels. It's hard to know if a user at a certain point in the application smiles because they want a toaster to stop. How do you feed that back to the person localizer model? It's not exactly clear. And in fact, I think you have to have some other source of labels to get enough of this stack built that you could potentially close a loop maybe on a smaller portion of it, something along those lines. And then privacy is clearly a serious concern with this application. You don't want to be sending videos from users' living rooms back to the cloud and keeping them for an indefinite amount of times. We've seen the architecture. Now let's talk about ways to get the data to plug into the corpus so that we could start to imagine training all these models. One thing that is very easy to do that you might think, well, let's start here is, hey, we're building a product. Let's take every person who works on the product and require them to go in front of the sensor and do whatever we need to do to get training data. Or here's an app, run it on your computer. Now, this is a really super biased way to collect data, and there's a whole bunch of reasons that this is going to be terrible. Number one is it's a small population, whoever happens to be on the team. You're not going to be able to fill out a matrix for all the different types of users that you might want to have using your product eventually. But it's not just a small population of people, it's a small population of places. Computer at a workplace is a very different thing than using it in a kitchen or something along those lines. Another problem, which is maybe a little bit more subtle, is that the devs on the system know how to set it up. They know how to trick it. Everybody's shared the secret of, oh, this is what we want the gesture to look like with the 2 fingers up and the 2 fingers half down. They're all going to produce data in the way that they envision the product being used, not in the way that the users who get the product eventually are going to use it. That's a strong problem that will greatly hurt the IID assumption and mean that the models that you build won't generalize nearly as well. Maybe another way to say it, maybe it's almost the same thing, is that the devs really want the system to work. They love it. They're working on it. They want the gestures to fire appropriately, and they'll do a lot of work to hold its hand, to really interact with the system exactly in the right way to get the result that they think they want. Getting data from the people building the system is really a poor way to do it for anything beyond just sanity checking that things aren't crashing. The next thing you could do is you can imagine setting up a lab. So you're a big company, you want to collect a bunch of data. Let's take a few office rooms and turn them into kitchens, right? Put the device there, put multiple copies of the device in different kitchen setups, get the lighting right, get everything right. Then you bring people in and say, please just do stuff you do in the kitchen, and we're going to record you, and that's how you could get that. It's somewhat less biased in that it isn't the devs who are doing it. It isn't at your computer, but it's really hard to simulate a lot of environments. If you were to say, hey, go build 10 kitchens in 10 different laboratories across your company, you'd be like, 10? That's a lot of kitchens. You sure we need 10 kitchens? And then you'd be like, well, we're going to ship this into 10 million kitchens, so probably we're going to need more than 10 before we're done with this. Another thing is that bring somebody into a lab, have a bunch of people with lab coats sitting around watching them, telling them we're trying to do something. They act funny. They overact. It's not super natural as people would be in their own homes. That is poor. Better, and potentially even better is that you would take the device and you would put it into the environment. So let's say you have 1,000 prototype devices and you get your 1,000 most representative users and give them the device and say, hey, just use this. Use this toaster. It's going to record some things. Be careful, not to embarrass yourself around it. And then we're going to send the data back to the lab and we're going to use that to train the system that we'll deploy to more people. Now, imagine a story where you take a bunch of people and you give them a device and you say, we are going to record this. We're going to look at everything on the recording. We are going to go over each frame with a fine-tooth comb in order to create a computer vision system. Please be careful. You've signed a waiver. You know that this is happening. You sign, don't wear a bathrobe. Or if you do, wear something under it. And just to say, people don't really realize these sensors and what the implications are. And even if you tell them very explicitly, anyway, give it to potential users for feedback. This can give you very good data if the programs run well. And to run this type of program well, you have to get the right representative users in the right environments. Like if you just sent it to people in Seattle, That's probably not as good as if you send it to people on the West Coast and the East Coast. It's probably not as good as if you send it to people in each of the countries that you want to eventually ship your device in, because styles are different, kitchens are different, devices are different, layouts are different, everything can be different. It's good in that you will give the user some instructions on how to set up the device, but they may not comprehend them or follow them all or interpret them the same way that the developers interpreted them. One thing that is really common is this notion of backlight. That is, take a camera and point it at a bright light, and anything in the foreground is going to be so dark you can't see it. I mean, just take your cell phone. Maybe cell phones are good, but take a webcam, hold it out in front of your face, put a bright window behind you with the sun, and see what your face looks like, right? And you can tell people, look out for strong backlights. They don't care. They don't understand. Even developers working on these systems have a hard time internalizing what is a backlight and how do I avoid it. Users are going to configure the system however they want. You may get back a lot of data that's not really, you're like, how am I going to work with this? But you got to tell yourself, this is what users are going to do. This is how they're going to set that up. And so if that's a problem for the product, then maybe the product is a problem and it's not viable. So starting to figure out how many users set up the device in a way that's just not workable will let you know if you need things like a special setup experience that guides the user through positioning the device and making sure the sensors are appropriate for the environment or something along those lines. Those are 3 ways to get data, and they're all fine. And of course, if we were going to close the loop, we have a 4th way to get data, which is even better in terms of having users using the product the way they're intending to use it and getting natural feedback on, is the product working? How's the user responding? Are they getting the outcomes that they want to get? Something like a spectrum here of things that you can do. In general, you're going to end up doing all of these if you're doing a corpus-based approach. I think it's just important that when you record data, you're very meticulous about where the data came from and what things you want to use each of these types of data for, because they're not all good at the same things, and conclusions that you make up here may not be correct here, even though this data can be quite valuable at building the product. Now, those are environments, but what are you going to do in the environments? If you don't have a product yet, you're going to have to ask the user to perform, to act, to follow some script, so that you have, like you're saying, look at the device and wave. That's the gesture we want to get training data for. So you're going to have users looking, waving, look, wave, smile. You're going to get a bunch of users going. Possibly not the most natural thing, but you need to make sure that each user that you bring into the lab gets you some form of meaningful data on the labels, the concepts, the settings, the interaction sequence that you're going to need to create your product. Hard for users to be natural or scripted. It's really, really, really hard. And the other thing is that users may do lots of stuff at home that they would never do in a lab. And those things are just like data that you don't get visibility into. It's a whole not IID in ways that you could have false positives on things that users do at home. And based off of your lab-based data, you're like, that false positive should never happen, but it's happening all the time. Just subtle little things you wouldn't even think about. Anyway, scripts are fine. Using the product as intended is better, and that's why closed loop is the best, but we may not be able to get there. But if you're doing a corpus-based system, you can still have users using the product as intended. They just have to be users in a special program who've signed up, who are giving you the data in exchange for getting to use the product, and who've signed a bunch of waivers, whatever it happens to be. Now, let me say that I'm not totally sure that all laws, that's true with all laws like GDPR. I'm not exactly sure, but you could pick people who that law doesn't apply to collect your data. Whatever you need to do, you need to do. But if you want to have them using the product as intended, you have this problem where you need enough of the product working so that users will even want to use it or be able to use it. If every time they do a gesture, it has like a 50% false positive rate, you're going to have to tune the UX very differently than the final users will get it. And so there's a mismatch there, which might make the training data less valuable. You need to have enough of the product built so that users can interact with the experience close enough to the experience you want to ship so that it's meaningful and the data is meaningful. But a problem here is that you have to build enough of the product so that it can be used even sort of like it was intended, which means you need to bootstrap your model somehow, or do some sort of, like maybe in a lab you have somebody behind the scenes pressing a button. When the user performs a gesture the way you want them to perform the gesture, you trigger that gesture was performed. That's maybe okay, but again, not as natural as you might like. And finally, you might come to, as a product team, decide that, hey, a wave gesture is not an unrestrained wave gesture. There's certain things. It has to start done, then it has to go in, out, in, something along those lines, and say that is what the product's going to respond to. Now, if you give the data collection experience to a bunch of people and say, take it home and please wave in a particular way because that's a training data we want to collect, they're not going to do it. They're going to wave however they want, you know? And if they're not getting the right feedback from the product to encourage them to do that, you may end up with a bunch of training data which isn't what you want. There's a lot of problems about collecting a corpus. This is a bit of a scratch of the surface. Let's go on and look at what you have to do after you collect the data. Once you have the corpus, you need to get the labels. And labeling is a whole process. It's going to require a lot of money in terms of developing tools and infrastructure, tracking, and finding people who you can pay to do all of the labeling work. But let's just dive in a little bit. And here's a sample of the tool you might build to support the labeling process in a computer vision application. Probably it'll have an awesome name. Maybe even awesomer than this one, although I don't know if you could come up with something like that. And then there's just the workflow around it where you'd say, well, on this image, is there a person or not? Or do I just want to go to the next image? If there is a person, you want to add a person to the tracking database somehow. And it's going to say, okay, now draw a bounding box around the person that you want to work with. As a labeler, you take your mouse and you draw a bounding box. And now that's person one. You could click add person again, add person 2, 3, whatever, however many people are in the data. But for now, we have person one. But as you've seen from the execution and the architecture, just knowing how to do detection and figuring out roughly where a person in isn't enough. So the tool might next say, okay, draw a bounding box around the face. Poor labeler has to go, okay, there with my mouth, I've drawn a thing around the face. Next, you might say, well, mark the hands, because we're going to do hand gestures. Okay, well, where are this person's hands on this frame? And you can imagine we're going to pretty quickly get into more things to mark, like annotate the person's face. So here's all the points that we're going to need for face localization on this particular user in this particular frame. Got to go further. You need to get the metadata. You need to track the matrix. Make sure you don't have systematic mistakes on any particular type of user. We'll get to that in a second, but you might want to know their skin tone, whether they have glasses, are they wearing makeup, do they have facial jewelry, are they old, are they young, do they have hair at all or not, or something along those lines. So for a particular person, you may need to enter a whole matrix of information. Then you may need to annotate things that aren't just within a single frame, but extend across frames. You might say, hey, this particular frame is the beginning, the first frame of a particular gesture. Then you might have to fast forward 30 frames or 70 frames or whatever it is and say, okay, now this frame is the end of that gesture. And then all the intermediate frames you need to annotate for these things, like what's changed. Well, probably not the properties of the person. That's probably once per person, but on each frame, you're going to need to redo this. And you could imagine having more or less tool support to do that. But that's what you need to do. And it's massive. It's an incredible amount of time. I've set up learning things that have set dozens of people working for weeks and weeks and weeks, sitting around hours a day, clicking stuff like this. And to get some sense of the magnitude, ImageNet, which has been used to get human level computer vision performance, is 1.2 million images. Oh, can you imagine? 1.2 million images. If you're going to try to be bootstrapping something that you can get to a closed loop, or maybe you're not trying to be quite as hard of a problem as what ImageNet is doing, you just want to say, hey, is there a hand here or not? That's possibly much simpler, especially once you've already localized to a region, saying like, I'm sure there's a hand here. Just refine where my estimate is of the hand. You could get by maybe with tens of thousands, maybe thousands to get something working enough that you could start sending a device into an environment and using natural usage to collect more information. But it's a lot of data. And you could imagine this poor annotator is sitting there and this is what they see. Just 150,000 more to go and then you can stop for your lunch break. But it's even harder than that because this is a tedious task. It's very error prone. is this the right spot for the eye, or should it be 4 pixels to the left? You could say, well, it doesn't matter, but what's important is that every labeler do it consistently so that the models learn based on consistent labels, so that you can tune the experience based on the output of the model with a consistent semantics. And all of that comes down to saying that you need to have something along this line, an agreement index, where you have multiple labelers per image and you cross-check to see if they're performing well. And this could happen just to make sure the semantics are the same. It could happen because these labelers are going to get tired, they're going to get frustrated, they're going to just be like, oh, I'm just going to do 15 fast, then click next, 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 and not update anything because they're just so over it. So you need to cross-check, and you could imagine having some agreement index that you show to the users and be like, look, your accuracy is slipping a little bit, maybe it's time for a break, maybe slow down, something along those lines. You could imagine if you were a meme company, you would also have a timer, like how many more seconds you have to finish this image before you're insta-fired. Don't do that. Well, I mean, whatever. Right, so this thing may be a video or an image, and if you're doing gestures, it's probably a video or at least an ordered sequence of images. So you could imagine this next button being a complete label from scratch that somebody else has to do. Or you could imagine the same labeler labeling chunks of videos where they're doing incremental updates, like click to the next frame, this person turns his head just a little bit, so all you have to do is drag the points over a tiny bit from where they were on the last frame. Maybe we even use a little bit of computer vision, like however good the computer vision system currently is, to do part of that update or to recommend to the labeler. So in that sense, you could have the system help build the system, but then you're dealing with this notion that labelers have to do this a lot and they may just give up and they'll bake in the mistakes that your current version of your system. Anyway, this is a deep thing. You could go around and around. You got to think about it a lot. The point is that if you don't think about these issues and invest, you're going to get out garbage labels and you're going to train a model and you're going to say, why is the accuracy so low? And you're going to trace it back to labels and you're going to say, oh, remember when we spent $30,000 getting these labels? We got to do it again. That's not going to be a fun conversation. So think about this ahead of time. The other thing to note, though, is that a single pass through labeling the data, you can potentially get multiple models of labeling out of one pass through all the frames. So it's also important to coordinate across the project. We'll see, I think, on the very next slide how that doesn't always work, but you can find lots of opportunities to multiply the impact of the work you're doing. In particular, label for multiple tasks at once, but also prepare for the future. I'm labeling this corpus today. I know I don't have enough processing power to run a particular model I want to do, but in 5 years on the next version of this device, maybe I will have enough processing power. And so I want to label for that anyway today and build up the value of the corpus once and leverage it over many years. It's a tedious job, but it can be fun. I found a lot of people are like, this is so cool. I'm helping to create this awesome product. I'm building an artificial intelligence. This is the neatest job I've ever worked on. So just keep in mind that we can each do our own job. We can align with our strengths. We can have fun doing what it is we like to do, because there are people out there who label and they make a lot of machine learning possible. Thank you all. Now we have the corpus. We have some labels. How are we going to build this menagerie of models that we need to produce the execution we talked about on that other slide, the detection, localization, tracking, recognition, blah, 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 blah. Here we have our corpus, and we're trying to train the person detector right now. It's easy to see that we need to select training data and testing data from the corpus. All right, that generalization, we already know that's probably even validation data. Probably you'd even want some of that. And you'd want to have particular properties about how you separate these sets. You want to make sure the same person is not in the training and the testing data. You want to maybe ensure that the same location or lab is not in the training or testing data. Everything we recorded from lab 1 is used from training. Everything we recorded from lab 2 is used for evaluation. If you don't do that, you're gonna be too optimistic. Another thing you want to do is look at the matrix of your important user types and make sure that they have good coverage in both the training and the testing data. You don't need to just do things purely randomly. You could say, I want to make sure at least 5% of the testing data has people with glasses, because that's an important enough case, and we're worried that not having an accurate enough model on glasses could ruin the product. We want to spend extra data testing that we've hit our targets there. Of course, that comes at a cost of having less for training, and you may need to go all the way back to your data collection process and say, we don't have enough data to fill out our matrix. go find people with glasses, get them into the lab, and record them doing blah, 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 whatever it is. That's how you train the person detector. But now you have to train the person localizer. And remember, the detector is run first. The detector filters out a bunch of images. There's a whole bunch of stuff in your corpus that the person localizer is never going to see. And what determines what it won't see is the particular correct and incorrect answers that the person detector makes upstream of it. So if you're going to train the person localizer, you're going to want training and testing data, but you want to train it with the distribution of data it's going to see in practice. So you're going to want to run this model first and only feed it the things that get past that model. To say that again, you need to select training data and testing data. But now you have these two additional properties that start to make this thing interesting and incredibly difficult. In fact, you don't want to use the same data to train the person localizer that you used to train the person detector. You probably can all see why that is. But if the person detector learns on a particular image to detect a person or not, and then when you run it on that image to give it as input to this model, it's probably going to do a better job than it would do running on a random image that you just pulled out of another part of the corpus. Now you have to coordinate what data am I going to label for the person detector, what data am I going to label and reserve for the person localizer. If you don't think carefully through this, you may end up having to have a multiplication of the data that you get, and that could be quite expensive. But maybe there's ways for you to exploit the structure in your model architecture to use a single image many, many times throughout the stack without bumping into this problem. The other thing is you want different users from the upstream model. Let's say you trained this on me, then you evaluated this on somebody else, then you train this again on me. That's another potential point for some bias or some over-optimism to get into the process. So not only will you learn models that won't generalize as well because they'll be solving the easy part of the problem where the detection thing lined up very well, but you also won't know your true accuracy of your generalization. So you might ship a product and it works much less well in practice. And, I've been using this person detector example, but maybe even more clear in the person localizer is that if you want to learn where the person is and you run the model on data that it was trained on, it's going to do a much better job of localizing the person in that image. Whereas if you run it on data that it wasn't trained on, maybe, this arm might be a little more crooked and the body might stop there and think it's a smaller person than it actually, little tweaks to the size of limbs or the location of a face point can have a massive systematic effect on the quality of downstream models. So if you cheat, you are going to probably regret it. Of course, in order to produce the features for training the person localizer, you need to run this model, throw away things that it doesn't detect a person in, flag the regions of interest, and et cetera, et cetera, et cetera. Remember, this is 2 steps, but in the architecture we drew, there were many, many more steps. So you got to figure out, how am I going to balance the risk of being over-optimistic with the reality that I really just can't bifurcate my data 15 ways and go collect 1 million training samples for 15 different sub-problems and go and hand label them all. In general, you probably need to coordinate the collection and labeling across all the subgroups that are working on all these different systems. And you need to invest in creating the full pipeline and making it very easy so that when this person wants to train their models, they can be running all of this stuff exactly like these people are building it, like the state of the art, the version they think they're going to ship, so that this guy gets the input that it's going to see in the product when the product happens. And there's clearly some challenges with this. One is to keep the data straight so we don't have advantages we won't have at runtime. But then the other is that the coupling between the models. So shipping a new version of an upstream model is going to require training and testing and potentially re-optimizing the feature extraction, the normalization, the hyperparameters, everything of all downstream models. I mean, potentially an upstream change could be explicitly better by every metric that the upstream team can see and just not worth it because of the effect on the downstream models. I've seen that happen an awful lot when you don't control the coupling between your models. You just can't ship things that you know are like you should ship it, but you can't ship it. And then there's even more potential of this coupling that in a system where certain actions need to be done globally, like the initial normalization has so much effect on everyone downstream, people might say, well, hey, if we normalize this differently, it would be much better for me because I need to see edges in order to succeed. Where another team is saying, well, hey, if you normalize it differently, it would be much better for me to succeed because I need to see tone colors or something else, whatever it is. So you might often end up with some decisions made at incremental points that are not optimal for anyone, but are workable with everyone. And it's hard to have those negotiations and even understand which direction to go because of the complexity and the coupling. Then retraining the models may take many hours or days to even take the raw video images and reprocess them so that you can get features for your model based on everything that happened upstream. And doing this and retraining, like cascading retraining of each model and retuning of things, if that's how you do it, which I'm sure you won't, could take forever. It could take weeks and weeks and weeks and weeks of just the computers running, and at the end, here's your new batch of all the models that are optimized. So in general, you're going to not be able to work that way because you're probably going to be under pressure to ship things, and you're just going to have to, each incremental change you make, you're going to have to just shepherd it through the entire stack. And it could be, I don't know, maybe that's not the right thing to do, but it's certainly something you need to deal with. It could be a big problem. Advantages of this intelligence architecture is that it can scale to teams. You can have one team working on localization and one team working on detection, and they can actually be very, very helpful to each other. You can see that detection could be a fast fail early, where localization can then take more time and spend a lot more effort finding where things are without having to worry about that upstream problem. So it can be very nice, and you can get different expertise applied to different parts of your problems. You also get efficiency at execution in the runtime because various models can be turned on and off, fine grained, but they can also share features between each other so that maybe 7 models can benefit from the same feature set that one piece of feature engineering code outputs. Certainly quite possible. And then you can imagine that taking this beyond the intelligence architecture and into the corpus-based approach, the value of the data sets can transcend the application you're working on. You can look at, I'm creating not a computer vision system for this one device, but a computer vision asset for my employer who wants to do more and more computer vision over time. That can be great, but then there is this notion that sensors are advancing quite quickly, so you have to be careful that you collect the data that in a way that future mitigates sensor changes that you might imagine happening. Resolution's going up, color quality is going up, low light performance is going up, infrared sensors are getting better and better and more ubiquitous, and et cetera, et cetera, et cetera. Now, I've mentioned it several times as we've gone through this test matrix, and I just want to belabor the point a little bit because it is so important to shipping large-scale systems that interact with users, is that you don't distribute the mistakes that your system makes unfairly onto any subpopulation of your users. Or if you do have to distribute them unevenly for technical reasons or whatever, that you're aware of it and you control the experience to account for those mistakes or to adapt for those mistakes. So you could say, well, here's your core user base. These are the people, the reason you're creating this product. And you can measure overall and be like, hey, my operating point is 0.1% false positive rate. So you can set that threshold across your core user base. That's fantastic. Ship it. You're good to go. That's such a low false positive rate. You don't have to worry, except for the fact that what about people wearing glasses? Maybe in infrared, glasses can have coatings on them that when infrared light shines at the glasses, so you can get infrared pictures, so you can do computer vision with them, they turn into these glowing orbs of death. And you got wah, like shining on your face. And so models that you build or things that you tune for users that don't have glasses might perform very, very poorly for users with glasses with the coating that tends to cause this problem. And you might find that people with glasses have a 10% false positive rate. Now that's not good. Right? Like you would ship a product and you'd be like, well, if you ever want a toast spread, first thing you do, take off your glasses and proceed. Right? That's just not going to work. So you have to think of something else. And there's so many possible things that could trip up your product. Computer vision, contours that are observed on faces with different skin tones could be different. The normalization you do might depend on skin tones. If somebody's wearing makeup or not, that could add or remove gradients or color profiles if you're not paying attention to it. Children's faces may have different sizes than adults' faces, so your normalization may end up with something that's much smaller than you expect. The backlit thing we talked about, you got to work with people who don't know how to set up your device, or you have to do something about them. So you have to think about when you're setting operating points. You don't necessarily want to set the operating point for the average case, which is your entire core user base. You might want to think about setting it for the worst subpopulation that you're aware of. And that might result in, hey, let's take the false positive rate for people with glasses to 1%, because we think we can tune the UX for a 1% case so that it's somewhat viable for people with glasses. That means everybody else is going to have a much, much better false positive rate, and the false negative rate is going to be higher. But what the heck? I mean, we have to do that. We can't ship a product that just doesn't work for people with glasses on. And when you're thinking about, is my model good enough to ship? Don't look at the quality bar for the whole population. Look at the quality bar for the subpopulations that you're worried about, or that you know about, or that you're interested in. And you should have, as you're developing your set of models, every day, every week, every whatever it is, for each critical subpopulation you're talking about, what is the false positive, false negative rate for that subpopulation at the operating point or thresholds or whatever it is that you're thinking of shipping. And make sure that the worst among all of those isn't beyond your quality threshold for where you've tuned the UX, or you could have serious problems. No matter how much work you do here, there's going to be something that you never thought of. Some other type of users, very specific thing, like a community in the Midwest likes to paint their walls a particular shade of color that messes up. I mean, who knows? You're never going to know. And that's not to say that machine learning is to blame for this. You will always have experiences that you've thought through for the people you know are going to use the product that don't work for other people. But machine learning definitely is going to have this notion where it's going to make mistakes, and those mistakes won't be uniformly distributed across every one of your potential users. So it's good practice, but as data people, we can do better than just kind of throw up our hands. We can measure lots of things. And if you think about measuring to find the risks or find the problems, you can look in your data and explore the mistakes with a critical eye and be like, what could happen if this mistake isn't random, but if this mistake is systematic? For every error that you look at when you're hand grading to try to improve your model, think about what could be causing this error and what's the worst thing that would happen if that's systematic and not just a random mistake. And having that mindset of what's the worst thing that could happen, what's the worst damage that I might have just caused to the world by creating this model, I find it very liberating. I love finding bugs. I think if you're going to be super successful at machine learning, you have to have some of that mentality where every mistake is not something to hide, but it's something to embrace and explore and use to get yourself better. But even within that, you're not going to be able to mitigate all the problems, and you're going to ship a product that has some gotcha, and you're going to want to find it as quickly as possible and go back and correct it before it causes too much damage. Remember, we talked a little bit about explicit feedback from users, and this is a great place where if you have an explicit feedback channel and you connect it to the right things in your system, you might be able to notice, oh, geez, you know what? This explicit feedback is all talking about a particular category of systematic mistakes that I'm making that I really want to stop making. Now, one thing about this particular architecture, and maybe corpus-based system isn't quite the correct title, maybe it's this chaining architecture, is that evolving it can be quite a problem. And we talked about even within building the models, there's tight coupling here, so it's hard to change this model without coordinating with the upstream and the downstream models, fine. But once your set of models produces an output, somebody's going to build a user experience based on it. And they're going to tune that user experience to the idiosyncrasies of your models, probably. And then, if you change the models, even if they get better, you may hit some problems with that. Now, if it's a first-party scenario, that is something within your company, something within your work group, some group of people are using your model to create a user experience, they may need to adapt when your models get better, even just when your models get different. Remember, new mistakes, you want to control the forcefulness, the frequency, all the things we talked about in the intelligent user experiences. And when it's a close by team to you, this is potentially okay. You can coordinate a joint release to manage the coupling. It's not always easy. It definitely can slow down velocity, and you'll find, I'm sure you've all worked at companies where you know that getting anything to ship outside of the 7 people you work closely with is actually can be quite challenging. But now imagine it could get even worse if you're dealing with third parties, people who potentially aren't even at your company. They're users, the apps ecosystem for your device, users who've handcrafted things around your device and use it in ways that maybe you didn't quite exactly attend ahead of time. Now with computer vision, if you're going to create a computer vision library, it could be successful. You imagine a lot of people would want to use it. But if you improve things here, you can straight up break third-party scenarios. Like, I've made my models better. All the work you put in is now flushed and you need to go retune things. Worst is that if you're doing constant evolution of a model service that provides this type of information, third parties might have constant unbounded work to keep their scenarios working in the presence of the changes you're making. And that's okay. Maybe some third parties will say, yeah, I'll do it because Apple ecosystem makes me a lot of money. So whenever they change stuff, I'll recompile my app fine. But maybe third parties will just be like, yeah, you know what? I got bored. I moved on. It's not worth it for me to run a business on your thing. So if you could instead tell the third party that, hey, we've created an API, and if you use this API, we guarantee some things that 99% of the changes we make, when we get things better, it won't end up messing up your scenario. Now, we're not going to go too deep into how to do that, but let me just give a little flavor of it. One way you could approach it is you could have versioning. And so you could have multiple versions of your computer vision service and be like, hey, we're at 2.0 now, but these apps were built with 1.0. So they can still call into the 1.0 interface and get back exactly the same information. This is possible depending on who's paying for the computation. If you're running in an ecosystem with multiple third parties simultaneously sharing one output, like if you're servicing maybe some first party scenarios and some third party scenarios, this might result in the first party using a newer version and the third party using an older version, and you start to think of, oh geez, I need to run that entire stack multiple times in order for all the apps in my ecosystem to get the version. So that may be possible, it may not be possible. If you really can only run one version, you might want to take an approach, kind of like the frequency and the forcefulness. You might want to dial the knobs way down and expose much less information to the third party. It's possible that you can do a lot of quantization, that is, really fuzz up the information you return. Third parties can still build all sorts of great experiences, but those experiences are much more robust to the changes you think you're going to make. So I go by this rule: never, ever, ever expose a raw probability in an API. That's just a recipe for disaster. Always use thresholds and do them in a way you think you can keep their semantics consistent over time. And if a single threshold's not enough, we've talked about this before, always you can use a small set of thresholds to expose different semantics to the client of your API. But this can extend from probabilities into other things. Don't expose raw locations. Don't tell them the pixel value is 17. Tell them, here's a block of pixels and I'm pretty sure the hand is there or the eye is there or something like that is there. And what this allows is that if a third party can write to a quantized version of your intelligence, maybe they don't care, the pixel is exactly there. They just care, is it the person on this side of the screen or the person on that side of the screen who's talking? Well, if you bake that into your API, then they can't possibly overfit to what you're doing so that as your models change, you get into trouble. You can also do this over time to hide jitter in your responses. If you remember that frequency where every time the probability value changes, output of different things to the user, well, think of that in the API sense as well, because otherwise your third parties are going to have to write a smoothing layer on top of your probabilities themselves. And if you can bring some of that into the API, you might avoid problems down the road when their smoothing behavior interferes with your ability to improve your models. All right, that's it. So we've covered a lot. Corpus-based learning. When you collect data, you can build a corpus if you have a very stable concept, or if you need to bootstrap so you can get to the point where you can do a closed loop. You might need to use a corpus-based approach when you have to collect data, when implicit labels aren't possible so you can't close the loop, when privacy is a concern, or when you need to bootstrap to a high enough quality level to get going. Data collection and labeling are keys to success in corpus-based, and you have to invest in them. They won't just happen organically. Don't tell people, go and put your labels in Excel and we'll figure it out later. You're going to have to build some tools if you're going to do something at large scale. Other learnings from this presentation on the intelligence architecture of chaining models is that model coupling can be quite advantageous in a lot of ways of sharing information, short-circuiting computation, but it creates coupling, and you really have to manage that coupling within your system, but also with how you expose it to third parties. And verifying machine learning systems requires understanding subpopulations and being very explicit to make sure you don't centralize all your errors in a bad place that could make your application unable to succeed. And finally, think about how you want to evolve your system and how you want to encapsulate information so third parties and even first parties don't have to deploy things as in sync with you as you're changing your models on a day-by-day basis. All right. Hey, I hope you enjoyed this one. Thanks a lot, and I'll see you next time.